Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I have the pleasure of introducing Murali Sitaraman from Clemson University. I've known Murali for more than maybe 15 years, something like that, from when he was editing a book with Gary Levins on some object-oriented specification and verification techniques. He's been involved in a project called Resolve, which has some 25 or so years on its that's been going for about 25 years. A joint thing between Clemson and Ohio State University. And something that really excited me about the Resolve project was when they started building tools, which was, I don't know, maybe 5 years back, and it was in fact Murali's group who started doing that. So he's here to tell us about some experiences from that. Welcome.
Thank you, thank you for coming to this presentation. Feel free to stop me at any time. We'll just have it to be an interactive discussion here. So I should say that this research is due to a number of people. This has been going on, like Rustin said, 25, actually 30 years maybe. And a number of professors and students from various places have been involved. Just like at Microsoft Research, it seems like one of your strengths is you bring people with different backgrounds to solve really difficult problems, and that's kind of what has happened naturally with this project. So we have people from foundations of computing to very practical people who are involved in this project. So it has shaped it to be what it is today. So before I do much of the presentation, I want to show you really quickly what the end goal here is. And the end goal is push button verification. And what you see on the screen right there is just some piece of code, all right? And this is what I'm showing you here is available freely through our website. So a number of students at Clemson as well as other institutions have used these tools over the past several years. There is a specification. There's just a piece of code. Here's the specification that particular code is trying to implement. And so by clicking the verify button, it essentially says, okay, this code is correct. All right, if all the things are green here, then the code is correct. If something is not right, then there's a problem, right? And you'll be able to see these little line things, little VC buttons on the left. And if one of them is checked red, then you can go and see, which one it wasn't able to prove, all right? So now back to the presentation here. The key here is really push button verification. Okay, that's what is different from what a number of other efforts have tried, and what Daphne is trying to do right now, and getting close. And there are obviously research challenges. So just to give you a little bit of context, there are several approaches. There are the ultimate goal is push button verification of at least functional correctness. I say at least functional correctness because in Resolve, we are also interested in specifying duration and space requirements. So you can actually show programs, work within specified constraints. And one of my PhD students is focusing on that. We won't get to it in this talk, but that's part of our bigger scheme of things. And and the other thing is, it's not just about some properties. We are really talking about full functional behavior. Okay, don't need anything Adobe. All right. So one approach, a number of people have tried it, is a variety of lightweight tools, where you prove certain properties. totally automatically, and you're with the goal of eventually increasing the set of properties you can prove. So that's one way to look at this problem. And the other approach, well, again, there are several examples, and you see some on the screen there. So the other approach, yeah, go ahead.
So what is that line? Because I'm kind of lost here. I mean, this is like the red line that goes up. So you have...
So this says they are increasing the degree of automation. Things are really, really automatic here. And then the goal is to increase more and more properties that are fully automatically verified.
But I would have guessed this, if you had not much automation, if you were willing to do things very manually, you might be able to prove even more stuff.
Right. So that's the other direction, basically. Okay. So here's another way that people have gone about, and Resolve and Daphne. I mean, you could put lines in between. I'm trying to kind of contrast two extremes, so to speak.
So there you make the turn?
Okay.
Do you mean for the degree of automation? Have you reversed the two?
No. Okay, so maybe the picture isn't as clear as we thought it was. Okay, so let's try it. So this, what kind of properties can you prove, right? So here you ignore automation. This is the second set of approaches, so to speak. We are going to try to specify, even if it's entirely manually, that's okay. All right, but we are going to be interested in specifying the total full behavior of correctness. And then the goal is, okay, someday we'll try to, automate things, some of these things, more things and whatnot, okay? There's, it's not something is wrong or right, it's just two different ways of, looking at the bigger spectrum of problems. And since Rooston is right here, he can either say, yeah, it's kind of true or whatever.
So this reflects some optimism in the sense that ultimately both methods will reach the Holy Grail.
That's the ultimate goal. We are trying to say that everybody wants all, who would say, hey, I don't want a lot of automation? Who's going to say, I don't want to verify full behavior? Everybody is going to say, yeah, that's what we want, okay? So there's some, end point that everybody is hoping for maybe, but it's just, we are getting there in different ways, and, here's the way we are going there, all right? So we put Daphne and Resolve kind of in the same category there. We are interested in specifying full behavior. And yeah, we can automate certain things, but can we automate more? And maybe we are heading there. So given that broad overview, the verifying compiler, Resolve verifying compiler, again, I should connect it to Tony Hoare's verifying compiler grand challenge. It's not so much to produce a compiler that's verified. It's to produce a compiler that actually verifies code is correct with respect to specs. Okay, so that's the goal. It's still an important problem to verify the compiler itself, but that's a separable problem. We are simply looking at, can we prove code is correct with respect to specifications, and there's a compiler. So the Resolve verifying compiler, this is a real crude approximation here. Essentially, there are program specifications in code, and you are verifying code meets specifications. And again, there is an important, interesting question that we don't get involved in, not because it's not important, just because you have to focus on a particular problem. Do the specifications capture intent? That's an excellent question. We should be researching that. Do they capture requirements and all that? We are not looking at that problem right now. We are simply asking, does the code meet the specs given that this is the specs? We are not saying code is right or the specs is right, just that they match, there's a mismatch. That's all the problem is. And then in writing our specifications and Resolve specifications, we are going to, ultimately software is going to involve all kinds of mathematics. Things that we have already specified, things we don't, and whatnot. So we need an extensible set of mathematical theories. We can create new theories, new results, and whatnot, and they'll be used by the prover. So overall, the Resolve verifier has this part, that's the verification condition generator. That's essentially here are the set of conditions necessary and sufficient to prove the code correctness. And then there's an automated prover that discharges those obligations using the results from the mathematical theories. So if small set of questions, this audience, these things might be obvious, but generally, in order to do this, you need a language that supports specifications in code. It's not going to be a meaningful exercise. We need to support new mathematical developments. Now, this may not be very obvious, and the implications of this are pretty serious. For example, a lot of decision procedures focus on particular theories and combinations and so forth. But if you think of this as a general system where all kinds of mathematics might be involved, then you have to question the scalability of approaches that are limited to particular things. Where is it going to end up? Because ultimately, large software is not going to involve one or two theories. It's going to involve all kinds of theories that are going to come together in your proofs. And the systems need to be able to handle that. The last point, if there's interest, we can delve deeper into it near the end of the talk. But I'm roughly going to say something like, the language should be designed to facilitate verification and should have clean semantics. For rough approximation, pure functional languages, let's say, have clean semantics. Okay, so the idea is, in imperative and object-oriented context, the idea is if you're reasoning about your software, you should be able to look at objects as having values from the mathematical domains you're using to model the types of those variables. You should not, in particular, have to think of objects as references in order to do your reasoning. Okay, routinely. Now, you can explicitly introduce references as part of your language, but routine reasoning should not involve references. And as you know, in Java, you do have to think about references to get your programs right and so forth. So Java, for example, does not have clean and rich semantics, which doesn't mean verification is impossible. It just means verification is considerably more complex than in a language that has clean and rich semantics. And just a claim here, I'll cite papers, or we can have more discussion. The result language is designed to meet all these requirements. Okay, so since all the people involved in it are academics or students and so forth, we have the luxury of defining where the verification problem is going. So obviously, I think no matter what problem we are working on, if we can't solve the verification problem under these conditions, we can't solve Java verification problem or whatever. Okay, so we should be able to solve it for languages, for example, with rich and clean semantics. If we can't even do it there, then saying we'll solve the general problem is going to be at least as hard, maybe harder. So a few more things about the verification. Obviously, verification needs to be sound. Meaning, if the system says the program is correct, it better be, or it better not be wrong. So, needs to be modular, and this is critical. This is a fundamental difference. And in this, in this audience, you probably aren't going to ask this question. A lot of people were talking about verification in the 70s and stuff. So, what's different now versus, what they had back then? One is obviously automation. The other thing is the systems of today we are talking about are modular, meaning you can reason about one component at a time. So it can scale up. And that is, a big part of the overall thesis here. And the last thing, the system needs to demand minimal justifications of correctness from programmers. So again, there are approaches, including researchers here in the University of Washington or Seattle, working on inferring invariants for programs automatically, and that is fine. If there are systems that help you produce those assertions, we can use them. Other systems can use them. But the thing is, the system, in general, those invariants cannot be produced automatically, so programmers do need to supply certain justifications for termination and so forth. But the goal is, we want to demand basically the minimal justification. You should be convinced, hey, your system should be able to infer these other things, okay, if we give these things. And again, the claim is resolve meets these requirements. Partly what we are saying is, if you see some assertions in this setting, then you are going to need it in general. It's not an optional thing. It's not that some other system is going to come out in the future and say, oh, you don't need these things. All right, it's not going to happen. It's part of the claim. So this, do a little quick exercise here. Just give you a minute to think about it. So to connect it with kind of regular programming and what we are doing here, suppose you had a queue data type with these operations, the DQ, NQ, and this empty operation, and you had to write this code, invert, to reverse the content of this. And we also tell you, hey, do it recursively. You can think for a minute, and you'll see, okay, I can see how to do this. All right. So now I'm going to show you such a program in Resolve. The syntax will be a little different, but it's going to be very similar to what you might do in C or Java or any of these other languages. All right. So let me just jump there. So first, here is the specification. So we'll go through the details. Is this readable from back there? All right. So invert is the name of the operation in our program. This is what we are going to call in our code. All right. And it has one parameter, which is a queue, just a classical data abstraction. And the ensures clause says that the output queue is a reversal of the input queue. Okay, pound queue signifies the input queue. One important thing to remember here is reverse is a pure mathematical notation. All right, it could have been written if our systems were sufficiently sophisticated, something like this. Okay, so that is the ASCII version of what I got here. All right. So the main point is you won't have a program where you're going to call reverse. This is just a mathematical notation on strings. Okay. So the specifications, when you write your specifications, the specifications have to be written in mathematical terms. But the parameters are programming objects. So you have to do this translation from, hey, this is a programming thing, but I have to write the specification in this mathematical language. So how do I do that? In Resolve, every type, I'm going to show you just a little bit of this, and then we'll come back to it. It has a mathematical model. So here I'm saying the type Q, this is a, an abstract data abstraction specification for a queue concept, and here we are saying Q is modeled by strings of entry. Okay? And this str is again just defined in string theory. This string theory doesn't come from physics, and it's not that string theory, and definitely has nothing to do with the string object in Java or anything like that. It's just a pure mathematical thing that we just called it strings. So in Resolve, every object has a model like this. And then all operations are explained using notations from that mathematical theory. So initialization, so when you create a new queue, it says initially the queue is empty string. Right, any questions at this point? So go ahead.
What's the example Q?
Oh, okay. So that is so in writing the specification, sometimes you might say constraints and the initialization, and you have to introduce a variable, a generic variable of that type. So the exemplar clause, it just means let Q be an example. That's the best way to read it. It just introduces a name for the formal system. That's all. It's like a, yeah. All right. But what we are talking, go ahead.
STR of entry is, so it's...
STR is like a mathematical function that's defined in string theory.
And it's a, what is it? It's parameterized by a...
It's parameterized by a set.
Okay.
And it produces, strings over that set, basically. It's like, sigma and sigma star, except the entry happens to be the parameter here. And there's no special anything attached to str. It's just a variable or, name declared there.
So finite sequences of entries?
Something like that. Yeah, except, finite sequences of entries would be the right way to think about it. Mm-hmm. All right. So I will get to these specifications in a little bit, but I just want to show you just, that the same ideas apply no matter what the types are. And so here, here's the specification of integers. And it says, the family, the integer type is modeled by the mathematical set, Z. All right. So part of the reason I'm talking about this is because in Resolve, verification of programs involving built-in types like arrays, pointers, integers, any of those things is no different from verifying programs that involve data abstractions like queues, stacks, or anything, because everything has to come with a mathematical specification of a model, a set where variables of that type take values. So here, integers are modeled by Z. That means all integer variables take their values from that set. All right? And sometimes it's going to have constraints, like here it says all the integers are always between minint and maxint, and then there are some properties involving minint and maxint that we know about, and so forth. All right? There are things like operation increment, and of course in our programming language we might have syntactic sugar like I++, which is really a call to this increment operation, for example. Yeah? So if you suddenly want to pretend integers don't have bounds in your verification, you would just come here and you might create a version where there's no requires clause for increment, and then suddenly you have integers. Okay, so the system is flexible, and it's pretty minimal on what the verification system itself needs to do. Doesn't have special purpose things for various problems. Okay, so now I'm going to go back to the solution to the okay, there is. This is the recursive implementation of reverse that we would have probably written. All right. So it says it verifies this. Okay. So part of the thing that we need to understand as we go through this is, what is it trying to prove to check the correctness of this code, right? So obviously we need to show that this is correct, whether you go through the, whether the if condition succeeds or fails. You got to show that for two cases. So if you look at the verification condition at the end here, this kind of went off the page. There are two verification conditions that correspond to this. There's more down here. We can't see it, all right? So it's saying you have to prove the ensures clause when the if condition is true, and you have to prove the ensures clause when it's false, all right? So it did those two. But it's saying I need to prove 4 verification conditions, where are the other things coming from? Well, one of them comes from the call to dequeue, because there must be something in the queue. So anytime you have a requires clause or precondition for an operation, then the caller is responsible for that condition. So it needs to be verified at the calling place. All right, so that got verified. And the last thing, because it is recursive code and we want to show termination, so this is an assertion that the programmer is writing, that they are saying decreasing length of queue. Okay? Again, a real subtle distinction here. This length operator is defined in string theory. It's pure mathematics. Okay? And what you put here for the decreasing metric has to be an ordinal in general. Okay? You won't write, for example, if you had an operation length on queue, you won't write length queue. That's programming. All right? So this is so in Resolve we try to keep the mathematics and programming cleanly separated. All right. So assertions, it's all mathematics, and programming, well, it's all code. All right. So let's do a couple of things here. So this interface, has been used in classroom discussions and whatnot. So obviously, you want to change things. So here, I can comment out these two things, and you can see how this code is going to fail to verify because it doesn't terminate. All right, and I won't really click the verify button because it does. The reason it would terminate here is we set a timeout, so it tries for that timeout. And as you can imagine, when you do this in our classes, most programs we write as well as our students write are usually not correct. So things, take, it's trying a lot longer than it should. So putting a time bound there seems like the reasonable, practical approach here. So I'll go ahead and click verify. Maybe I'll do it at the end after pointing out a couple of other things. Let me do one other quick thing here. Look at a verification condition. So this button just generates the verification conditions.
So why exactly does it take so long?
Why does it?
Because you said that if you comment those lines out and click verify, then it takes very long, right? That's what you said.
It doesn't take super long. I mean, we'll do it. Just that it takes a little longer than I want to wait for it in this talk. And it just tries to prove, using various theorems, that whatever assertion you have given is true. And it times out after a while at trying various things. So when it proves, it knows it as a proof. It can produce a proof certificate or whatever. When it fails, there are many reasons why it didn't prove, and one of them, in this case, is like a timeout. It doesn't try to establish the negation is true or something like that. There's a more difficult problem in general, so it doesn't try to do that. It's just trying to say. Did I answer your question at all? Or maybe you are asking a completeness question and.
Just
an efficiency
it
question.
would seem easier, or that you could finish sooner.
Yeah, I mean, proving that the length of...
Yeah, here all it has to do is length of queue is less than length of queue. And, so let's go ahead since we... Yeah, so what all is it going to try to prove? Yeah, it's going to fail because it can't prove length of queue is less than length of queue. Okay.
Why does that take long?
Because it just thinks there could be some theorem. It's trying various combinations of things to try to prove maybe such a result is possible. Who knows? Might be obvious to us, but it works with a set of results, and they can run out.
clear. Like if you're trying to prove something and you never try to prove the negation, then potentially you could just try forever.
Like, you know, it could be just that there is this particular definition or theorem sitting out somewhere that if you just got to that one particular piece, you know, maybe this less than will magically disappear and something will happen. See, everything is it just knows a bunch of results. And this is a fundamental difference between this prover and say a symbolic, you know, the decision procedures or whatever, where they can try to look for a counterexample and stuff. It doesn't do that, okay? So ideally in the future, a system could combine this and say, hey, if there are errors, first try out the decision procedures, and if it's wrong, tell them quickly, okay? But that's not a problem we are interested in solving. It's, you know, it's a useful thing to have, but it's not, you know, anything we are interested in solving.
But isn't that a problem in practical use, that you never know when to stop?
In practical use, okay, so I'll put up this slide on completeness. Maybe I'll go do that right now. And, okay, yeah, so this is what we are talking about. The tool is sound, okay? It's complete, it's incomplete. The current version as well as the eventual version will be incomplete for many reasons, okay? The simplest reason is that, for example, when you wrote a loop invariant, your loop invariant wasn't sufficiently strong. Okay, so it wasn't adequately justified. So your code might be right, but the loop invariant wasn't sufficient for it to prove its correctness. So it might say, oh, your code is wrong. Okay, or the system we are working, you know, it's a research system, so we continue to, you know, enhance our mathematical developments and stuff. So it's something that might be very obvious. You know, say we just forgot to put in something like string concatenation is associative. Okay, that's just a theorem that it has in its library, and hey, I can't get that result. So there are things that are provable, but because my mathematical development is inadequate, I can't prove certain things. Okay, so again, I would discuss this more as a transient problem. Okay, so once the theories are more completely developed, things like this won't happen. All right, web ID timeout that I just explained, because you know it tries a lot more things than it should, and a lot of times if it can't find it quick enough, it's probably, you know, something is not provable. Okay, so we got a timeout, so it might come up. And then the fourth point is backend provers are efforts in progress. So there are things that our prover from 2 years ago couldn't prove, but today's prover can simply prove it much easily. So because this is research work in progress. And the last one, this rarely arises in practice, but there's potential for there. Okay, so the bottom line, if it says X I can't prove, it could be any of these reasons, and that's what it happens there. And yeah, sometimes it's quick, sometimes it's not. The other thing I wanted to say was, let me go back and. So can you see this part at all? So one of the things it's trying to prove is if you reverse Q prime concatenated and then attach it to E prime, that is reverse of Q, right? And one of the things it knows from the context is that Q is really E prime concatenated with Q prime. Okay, so the way it's going to get there from here is because it knows this theorem. Okay, this is what I was trying to get at, that there is if I log in here, if you go to the components, so you see one other thing, theories, and then there might be string theory there. It has whatever results it is using, and somewhere there probably are results involving concatenation with reverse, for example. Can you see that? Okay, so that's the theorem it's using. So there's really no magic behind this whole thing, right? It's just using all combinations of theorems. And part of the whole exercise in this research is that we can write a lot of the specifications we have to write in software without using explicit quantifiers. Okay, I'm going to show you a sorting example. Okay, typically something you think of where you think, oh, there are going to be quantifiers in the specifications. But if you set up your mathematical developments suitably, then you can write specifications that involve no quantifiers or anything like that. And a pretty much simple rewrite prover can actually prove your sorting, a generic sorting code to be correct. Whereas, still a pretty big challenge for all the other decision procedures and everything. Okay, because it can do things given the set of theorems in a context. Yeah, go ahead.
So you don't have quantifiers
In your specifications. You can write quantifiers, okay? So your theorems are going to involve mostly, hopefully, a lot of them will involve universal quantifiers and everything.
But your prover still doesn't have it.
But the provers wouldn't have to instantiate them for the most part.
Okay, so you have your specification with no quantifiers, but your prover still doesn't have it.
No, not that it doesn't terminate. I mean, it's just that, see, the purpose is if the thing is correct, you want it to complete with a proof. If it's not correct, then, who cares the most? Okay, not that I'm saying who cares. You can use one of the other systems to help you find, okay, it's going to say I can't prove this. So you can say, oh, that one it can't prove. Now let me run my decision procedure if I have one for that and find out.
I mean, when you are using tools like BCC or Daphne, it does not rely on completeness of decision procedure.
Right.
It does not rely on that. It actually, the theorems like you have them there, you
Right.
actually tell them when should it apply them. You actually tell the tool, and when it runs out of theorems like that to apply, then it stops.
Right. See, we don't do it. See, the programmer doesn't do any of that here, right? So the programmer simply writes the code, and the VCs are generated, and the prover, takes over from there. So it's a very different thing from trying to say, let me help you find bugs. That's not the goal.
Wait, in this case, also the VCC or Daphne user also does not provide those.
Yeah. Right. Yeah. I mean, this approach has the advantage of finding a class of bugs easily. Okay. So that is an advantage, right? Yeah. That.
Both BCC and Daphne are used for verification, not for finding bugs.
Well, okay. See, this is what I was trying to explain at the beginning. So if you go to the general system, okay, where the programs are going to involve higher order assertions and involving all kinds of theories, it's not going to be possible in general for you to come up with your, you cannot get your provers to prove them when they are correct.
So maybe
But-
I can ask a
yeah.
question. I mean, going back to that original slide, the different trajectories.
Okay.
I think it's something like cock as being very much to the left on that graph there. Whereas it's got all kinds of higher order capabilities, so it's not very automated. And it seems like Daphne and BCC are actually a little more automated. And I'm kind of wondering, so where do you see resolve as fitting in here?
Yeah, so resolve is from the programmer perspective, okay, in terms of verification of code, right? We want it to be purely automated in the sense if your code is correct, it's going to produce a proof.
That's assuming that the programmers put in
The invariants and stuff. That's correct. And what is not automated is like the theorem that I just showed about associativity of string concatenation or whatever, right? Those are in the mathematical realm, and they may not have automated proofs. Okay, so for them, people may have to write explicit proofs, and there might be a proof checker that checks your proofs are legit. So in the mathematical realm, those proofs are not, our expectation is not that they would be automated, right? So in the programming world, if you had sufficient results and your code is properly annotated, then the proofs will go automatically.
So that may be actually fairly close to the style of using Delphi and PCC, where you kind of say there's some lemmas that we're going to write that are not runnable, and then those will be called from the...
Great. Just the proof method is very different. See, this is a simple rewrite prover. It's not a decision procedure. Okay. So maybe I will do the sorting example, and then we can come back and ask this question again.
So by the way, those theorems, do you actually prove them? So do you prove those theorems that you have there in result?
Yeah, that part is not implemented. Yeah, they should be proved. Right now, you could put in bogus thing.
Those are really axioms.
Yeah, right now, but it's not meant to be that way. Okay, so part of the thing is, so there's a PRESI, which is like the interface of the results. Here are the results, and then there's supposed to be a module that is proofs for the results. Okay, so that part is not done today, and hopefully we can leverage Coke or some other system to help us do that part. Yeah, so let's is it big enough? Little. Okay, so here is a specification of sorting, right? A sort queue operation. That's what you want to specify. But you want it to be sorted basing, any total pre-ordering relation. Okay, so it's parameterized. So this specification is parameterized by this LEQV relation. All right. And then the sort specification says, well, two things. One is that the output queue is a permutation of the input, right? And then that this output is conformal with this relation. So from the user space, all the quantifiers are gone. Okay. Now, if you had sufficient results involving these definitions in your mathematics, then the verification conditions that arise can all be discharged automatically. Okay. We don't know of any system that can do this automatically. Okay, you generic sorting one like the one I got here. So let me show you the implementation here. Okay, so
Why do you say that? I mean, I know of many tools that could do this.
This where you provide the code and specifications for a generic sorting with the
So what the main part that you're thinking is tricky is parameterizing by the relation?
Yeah.
Okay, so I know some tools that
Yeah, you can tell me which one, and we can see what they can do. Yeah, it'll be interesting to see that.
even Daphne could do it, I suppose.
Yeah,
I mean, as in, those are the tools we're talking about right now. So I'm sure Daphne and maybe even VCC can do it, right? If you take a function as a...
Yes, you can take them up.
Take a map, right?
Like Net Star.
Net Star.
There's a number of them as well.
So Daphne can do higher order, you can write higher order specs in Daphne and they would...
No, but you could have a module that would say that you want to have a type and that it's going to have some operations and you can state some properties about those operations. And then you could have another client that uses that module without knowing what those operations are.
Oh, but see, we don't have a client. It's not instantiated.
No, well, you don't have to instantiate it if you don't want to, but you would also, at the place where you do instantiate it, it would then prove that the appropriate properties do hold.
But I don't, yeah, the problem is you can't instantiate it.
But
Okay,
we're not talking about
because you
instantiation.
want to verify it for a generic relation with, whatever properties.
So you would.
I don't know, I would like to, I mean, if there's such a thing out there, I would very much like to see that.
Excellent. So, I mean, that would be, as we have some one-on-one discussions, maybe that'd be great.
Yeah,
to see
after
the
the
various tools
session,
we
yeah,
have.
I mean, that sounds like a
I can show you-
perfectly,
I can show you something tomorrow that does.
okay, yeah, I mean, yeah, it will be very interesting to hear about these things. Yeah, we did hear about, there was a presentation we went to, somebody said they could do it, and we, looked it up, and then it didn't really do it, and then they said, oh, it has these restrictions and these restrictions. Oh, by the way, you have to do this, and so yeah, will be interesting to see. Again, the general thing here to see is, see the specifications are going to involve higher order assertions, okay, in general, and they might not live in one theory or the other in general, because if you implement, a data abstraction that is conceptualized using strings or trees or something, and another data abstraction that uses a completely different theory, then your correspondence, which is the subtraction relation, that's going to involve multiple theories. All right. We do not know of any approach that would automatically, go across multiple theories like that. And so there are, I think, I'm talking about a couple of, orthogonal problems almost. Okay, one is the generic part of this particular example, and the more general problem of bringing in theories that are, not designed originally to be composed or something like that. They all, have been developed, and then, the assertions involve multiple theories. We don't know of any approach that can do it. So will be, super interesting if somebody say, here's, here's the silver bullet. I haven't heard of such a thing. All right. But the other thing is writing these specifications, without the quantifiers. It just requires a lot of mathematical developments. But as you can see, you can do it all without quantifiers.
So just to read the code a bit, you have procedure sort updates queue, and the parameter to the queue is implicit entries.
Yeah, so this is a generic queue. So yeah, let me go back and explain. So this is in the context. So you start out with this specification, which is the specification of queues, where queues are mathematically modeled as strings and stuff, right? And so this comes with a basic set of operations that we have defined. Again, nothing very special about them. So here are the basic operations we got for these queues. But then you extend it with other operations, and the one we are talking about here is the sort operation. Yeah, so so this is in the context. It says this enhancement for queue template. So the specification of queue, where we said queues are mathematically modeled as strings, is in this context. So that's why we can treat this Q as though it were a string in the specification.
And what is B Boolean?
Yeah, B is a Boolean.
Okay.
Yeah, and it's the math Boolean, not the programming, right? Yeah.
Is there much difference?
Is there a difference?
Yeah. Oh yeah, huge.
What is the difference?
Oh, okay. I mean, for us syntactically, it'll cry like crazy. As I said, the specifications can involve only mathematical things, and if you use a programming thing in a specification, then it looks for the corresponding mathematical model. Okay. Obviously, we have a Boolean template or whatever. Okay, where it says, oh, this Boolean is modeled mathematically as the mathematical Boolean. But there's no I mean, you could happily decide you're going to model your Boolean type in your program, right, with integers, with restricted to 0 and 1 or something like that, and the system wouldn't care. So these are two separate nations.
Is B the two-element set?
Yeah, B is the mathematical, Boolean, yeah.
So I'm curious, this separation, why? I mean, do you have an advantage, or is this just a matter of...
Yeah, absolutely. So the thing is, the mathematics, so there are a small collection of mathematical theories we are going to reuse in the specification of lots of computer science concepts. For example, the idea of strings. We have those theorems and everything. I'm going to use them in specifying queues, stacks, lists, whatever. So a number of programming things are going to use the same modeling, and then all the theorems and the results I have set up for that come for free. Yeah, so there's a huge win. You want to?
I mean, it depends on the abstraction level that you think of in
Oh, yeah.
a programming language. But if I use sequences in a programming languages, I don't feel like they're any different than my mathematical sequences. I don't feel like I have to distinguish them necessarily.
No, see, the mathematical things don't have any notion of them being implemented, okay, or being implementable or anything like that. Sure. Okay, so the programming concepts you write, obviously you can write unimplementable specifications. Okay, so let me see if I have actually a sequence template or whatever here, and again probably that there I'll model the sequence as a string with, yeah.
But do I care? I mean, do I care if it's...
Yeah, I think you very much care. Because like I said, see, the mathematical world, you set up a bunch of theories, and then you have the results, and you have proofs of those results purely in the mathematical realm. And you do that once and forever. But the sequence concept that I write in the programming world, I could implement it using any number of ways: arrays, pointer stuff, linked structures.
But when I use it, then it's all the same.
Yeah, but see, then in writing the specification, how are you going to write the mathematical specification? I mean, you can say, I have a mathematical notion called sequences, and I have a mathematical notion, a programming notion called sequences, and I just happen to call them the same, and they match in this case. But see, what you don't want to have to go to is every programming concept has a corresponding, mathematical.
No, I mean,
So this is basically the reuse kind of thing that I want to create a.
But for any mathematical concept, you could also give the programmer a default implementation that is exactly that mathematical concept.
But see, the names themselves in our heads don't match. Okay, so math guys have don't have stacks, queues, and all that stuff. Okay, so that's all.
So I just personally, I like to not think of them as separate roles. I like,
I mean, we have found it to be very useful, and reuse being one of the many reasons for doing that. Yeah. So, yeah, I don't know if I answered your question.
Well, I wanted to see eventually how you were deciding this LEQB relation in your code of sorting.
Say that again. Now you're talking about a client code or the implementation of it? Right.
Sort,
Let's
actually.
talk about the implementation again. Talk about that. Yeah. Okay. So this code, sort is the only procedure in the interface, right? But there's also a local procedure here, which we have implemented, I guess. So there's a remove min operation. Okay, that again you can see the specification. It removes the minimum entry from the queue according to the relation. And then this gets used in the.
How is it doing that? Is it LEQB is a mathematical thing, right? So I
Right.
can't call it in my program. It's called compare.
Oh yeah,
Let's
good
compare.
point. Yeah, okay, so that's the, yeah, good. Yeah, I'm glad you pointed that out. So the programming code, see the specification does not need an operation to compute the order, right? So this is the particular code that the programmer is going to pass, and the specification of this obviously uses the LEQB relation from the specification. So I'm saying, give me a compare procedure that satisfies that relation. And then that compare is going to get used, yeah, somewhere in this code.
And compare is a pure function.
There is no notion of a pure function, but it is because it restores the parameters, meaning that the parameters aren't changed and it returns, a Boolean type. It's like a pure function, you can think of it, except you can't use it in assertions. It's just a programming operation that just happens not to affect its arguments and returns a value.
But you say compare equals LEQB of E1, E2. So compare, but I would expect it to at least be compare of E1, E2, right?
Yeah, so this is essentially understanding the syntax here. So when it says compare, whenever you have a function result, you want to read it like something like this. This is really saying result of compare.
Applied to E1, E2.
No, result that this operation returns. See, this returns a Boolean. Compare returns a Boolean. Or saying the result that compare returns is what you would get from this. So, you could have equivalently written this as something like, this is not going to syntax check, but then
So compare is
or something like that.
it's compilable.
Compare is just a placeholder for the result of the operation.
And what the operation does is it just gives some implementation of LEQB.
Right. So that's what the user is expected to provide, some implementation of this operation. Right. Right. So so what I quickly want to do is kind of jump a little bit and show the client end of the world here. Basically, in proving this, it uses various theorems involving permutation, and things are comparable and things are universally related, and there's a number of theorems involving those. Okay, and you have enough results, it can discharge all those VZs automatically. Right. I'm going to kind of jump here and show you kind of the coding end of the world. This version is the one that we end up using in classes and whatnot. It's frozen from a few years ago, but it has some features that the research version doesn't have, which is always work in progress. So here is so this is a meagerly specified client code, all right? So something that uses queues, and so there is some record described here, the student information with a few fields or whatever, and then these are the two mathematical definitions. Okay, so in Resolve, definition means it's a math definition, all right? Operation and procedure are the words that go with the programming thing. So there is a there is a definition to compare ranks. There's a definition to compare ages or whatever. And then here's an actual operation where you say, okay, my operation will ensure that it returns the LEQV according to rank. All right, and this is just regular code here. This colon equals is an assignment, so it says, yeah, it's just a regular code. Here's the spec, and then you create an instance of the Q template. You enhance it by the sorting capability. All right, and there you pass the mathematical definition by which you want things to be sorted. Then you pass the programming version of how to do it as a parameter to the implementation, because only the implementation needs that parameter. All right, so making any sense here? So this is where you're creating an instance, and now if you declare a Q down here, you can not only call the regular Q operations, you could also call the sort operation. You have enhanced it with this additional thing. Right. So the compiler, let me just show you this.
What order did it use here?
Say that again?
Which sorting order does it use here?
Yeah, because you have passed the rank LEQV. So you're saying, I want an instance of the Qs where I'm using this, right? So presumably, so this example, I put in 3 things with ranks. S1 is 2, 3, 1. And so this one, let's see, let's build it. Oh yeah, the program ran and produced 1, 2, 3. I don't know if you can do this. So we went through all the stuff to take 3, 2, 3, 1, 2, or whatever I took, and produce 1, 2, 3. All right, but
Is it possible to run the verification also?
we can generate the verification conditions, but I don't think I can pull up the, oh, in fact, I edited the stupid thing in random ways, so it's saying errors. The verifier can be run on this version right here, but we have run it and it has proved all the VCs. It just takes a bit longer than the time hours we have set. And so on this version, it's just never going to, some of the VCs it's not going to prove because it's just going to run out of time. We set the timeout to be short enough for most purposes. But there is, Hampton Smith's dissertation has all the proofs and everything. So the complete.
I mean, I presume we're not talking milliseconds, and you would have increased it by a few. But are we talking minutes?
No. There's like there are a couple of there are like 1 or 2 VCs. I wish I could tell you exactly. Hampton's dissertation is online. So there are like a couple of VCs that are just a little far to reach or whatever, that it takes more time, and then it won't come back on those, and so that's the reason. But having said that, since Hampton graduated and he's gone off to Google for a better life, we have actually basically changed how our prover works. So Hampton's thing did it's a backtracking type of prover that he did. So as a proof of principle, how far this approach can go, we did that. So the version we are working on now, it takes advantage of congruence classes to simplify a lot of things. And yeah, I had the discussion with the student who was working on that right now, and it seems like that's going to solve things way faster. We don't know. We haven't. It's kind of under development, and we are experimenting with it on a variety of examples. But so later this summer there might be a version where all these things go automatically pretty easily.
To come to Rustam's question, I mean, with your previous students' work, are we talking seconds, minutes?
I'm really poor on these things. In fact, the best, if I don't want to say anything wrong, the best thing to do is when we go off, get online and write at our Resolve website here. So there is a research site here. And one of the links there is his dissertation. So all the results are, the exact numbers are there. So I should just look at that before I say anything. But again, the bigger point is, I think, more like this, that if your programs are properly engineered, so to speak, okay, and they are documented, then the provers, the automated provers, themselves don't need a lot of deep thinking or anything like that. If the mathematical developments are sufficient, then you can write these specifications. A critical thing being, if the provers have to instantiate quantifiers in all different ways and everything, then that's a major bottleneck for automation. So part of the whole thing is, if we can move that problem away and write our specifications, okay, where you use these higher level mathematical constructs and you have suitable developments involving those, then it is going to be doable, with a simple, more or less simple, rewrite. I don't know if I want to call it real simple, but it's a straightforward, so to speak, rewrite type of prover. Should be able to prove most of these assertions. The last couple of things I just want to, in case you're thinking about these things. So we were kind of looking at things from the user end of things. In Resolve, of course, you can write implementations of data abstractions. So here is an implementation of queues using what we might call like a circular array realization or whatever. And these data abstraction implementations, programmers really just have to write two assertions. One that we call a convention, which is like a representation invariant, all right? And another is a correspondence, which is an abstraction relation that relates the underlying data structure to the abstract model, all right? So given those two assertions, all these operations would be, that's all will be needed to establish the correctness of these operations. Again, the version we have available right here, it will generate, only verification conditions at this point. We can't prove them more than anything else because our arrays are modeled using lambda functions, and we don't have enough theorems involving those. So there are enough things here that are sufficiently hairy that it can't discharge without those theorems. All right. So again, it doesn't seem like it's a showstopper or anything. It's just getting there. We just haven't gotten there. One last thing here. So Resolve is set up. The language has been designed so that the programmers don't have to think about references or anything for most of the programming, because, like I say, when you have a queue, it just has a value from the domain. It's a string of entries. That's all you're thinking about. All right. So the language does not have like an assignment construct where you can assign or alias one queue to the other. It's not like a built-in thing. But having said that, there is a pointer concept in resolve. So if somebody wanted to create pointers to things explicitly, then they can go ahead and create them, and surely those implementations would be, probably a lot hairier to verify than the more general implementations. And as a result, our examples using, where you might see assignments, you will see, for example, so in resolve, we have the swap as the basic data moment operation. And so this is like a stack flipping operation. So you pop everything and put it on a local stack, and when you get done, you can just swap the result. This colon equals colon is the local swapping operator. So you can use it to exchange the values of these objects. So underneath, of course, that operator is implemented as exchanging the pointers to the all objects. And all objects in the compiler are represented through pointers, all right? But it's just that from the user world, they don't have to think about that pointering in their reasoning. And obviously, this is a huge level of simplification because it restricts where you have to reason about references and pointers to within a few components, as opposed to it being something that is part of all reasoning that you do every time you make calls. So I think that, is probably a good place to stop here, and I can, I'll just get you to the very last slide here. Yeah, so here are some of the things we are working on. I already mentioned specifying performance and generating verification conditions for that. So there is a performance specification language that goes in addition to what we are looking at here. There is still quite a bit more research that we are doing in the supporting math type systems. Because as you can see, how you have to talk about sets and classes and stuff, because resolve includes machinery for writing any mathematics. We have to kind of draw a line between what mathematics you can write in resolve and what is outside of it and stuff like that. So that's part of what Blair is working on, and the automated prover, this next version of it, that's the focus of Mike's work, and Sammy is working on reasoning about programs that involve reference behavior. Right? So I think it's a good place for stopping. Thank you.
Let's see, we've gone a long time. I have a question, but maybe someone else.
Yeah, and again, thank you for all the questions you asked. Hopefully, we can follow up on some of them, and I would really like to hear what other people have done on some of the problems we have worked on, and again, you have to kind of realize that the devil is in the details, and a lot of things that look almost the same turn out to be very different. That's been our experience, and so, all right.
So I think Morali's going to be here today and tomorrow. Some of you are also already. And if you want to, we can set something up as well. The question I was going to have, but it's probably better to discuss offline, is instead of using your own handwritten rewriter things, I mean, there's mod which does rewriting, for example, and I think that many of the things could use Z3 with quantifiers to do rewriting in a probably in a similar way to what you're doing, but
I think, yeah, ideally, I do think, going back to the question you were asking here about detecting errors, yeah, I mean, I didn't say it at the beginning. The system that I demoed here, this is all was done at Clemson. We have a group of people at Ohio State working on, similar systems and, provers, and as well as they focus on also, reporting back on the errors and stuff. So their system, for example, has a back end of their own decision procedure, as well as it has Daphne and I think one other system. So they got a bunch of systems hooked up to their back end. So basically what they do is they just run them all on a system when you write this program, and whichever one comes up, if one of them says there's a bug, there's no reason to run anybody else, okay? So you just stop right there, and maybe that system will give you what the bug is, and then you go from there. So ideally, I think all these systems could be maybe hooked up to your back end, and then you could try them all. And I think that would be ideal, because you do want to, when things are wrong, you do want to get the feedback as quickly as possible. Yeah.
Okay. All right. Thanks again.
Thank you.